synthesis of phenol and acetone are linked. And so the first thing to recognize is that you start out with an aromatic hydrocarbon. Okay? An aromatic hydrocarbon is something you get from petroleum. Okay? So you end up isolating cumene, which is this stuff here, from essentially from petroleum. Now, one of the photons in cumene, that one, is different from all the rest. That's benzoic. There's only one of them. And so when you treat this with oxygen, usually this is done with the presence of a catalyst. Oxygen behaves as if it's a diradical. Okay? And oxygen is a very strange molecule because it is a diradical in its electronically lowest state. So what we breathe is essentially a diradical, and that's one of the properties that it has that makes it so reactive. So what happens is oxygen pulls off this hydrogen atom, and you end up getting a hydroperoxy radical. That's one of your products. But the other product is this benzoic tertiary radical. Now this is going to be resonance stabilized. I don't need to show all the resonance structures. You can do that. And so this is going to be, and it's tertiary. So this is going to be a particularly easy radical to form. Now what happens in the next step is that these two radicals combine. Okay, so they're formed in close proximity one to another, and so they undergo radical recombination. So you end up with this as your product. And this is it's not a peroxide, it's a hydroperoxide that has this cumene group. So this is called cumyl hydroperoxide. This is, I indicated last time, a state. Okay, so cumyl hydroperoxide is something you buy. It's an article of commerce. It's used as an oxidant in chemistry. When you treat this with catalytic acid, here's what happens. You end up protonating indiscriminately, one assumes, both oxygen atoms. However, at some point, the end oxygen atom gets protonated like so, and you end up, and this is reversible, I should show that. And you end up with this as your intermediate cation. So what happens next is something that we've seen before, but not with oxygen. We've seen a migration of an alkyl or an aryl group, a cationic rearrangement. But typically, what happens is the alkyl or the aryl group migrates from adjacent carbon atom, not from adjacent oxygen atom. So this is different for us. So you take the phenyl along with this bonding electron pair, migrates to that oxygen and displaces water. So it's a cationic rearrangement, but one that's a little bit different because the rearrangement now takes place to oxygen, not to carbon. And so one of your products here, of course, is water from this. The other product, notice, is going to be this carbon atom with a positive charge. So I'm left with this carbon atom positively charged, and then I have the phenyl, which is now migrated to oxygen. Now, this cation is a particularly stable one, and you can see that it has a resonance structure of the type that we've seen before, where I have a positively charged oxygen atom, but I also have atoms that have complete octets. So this is going to be the important one. And so this species is going to be particularly easy to form for two reasons. First of all, remember that the oxygen-oxygen bond is very weak, and the product is stable. And so for those two reasons, you can imagine that the process that converts this hydroperoxy conjugate acid to this cation and water is going to be a particularly easy one, right? You also are going from one compound to 2, so you have an entropy advantage. So this is a very easy process to do. Now, the water comes back and reacts with that cation. And so water ends up reacting with that cation to give a compound of the type that we've seen before, actually. This is very similar to something we have seen in the past. And so, and something that's going to be the subject of the next chapter. Now, proton transfers can take place very easily, right? And so I don't need to show water coming off and abstracting that proton, and then the electron pair from here picking that proton up. But that obviously can happen. And so in a series of reversible steps, I can go from this cation to this one, where all that's happened is proton transfers. Remember, those proton transfers take place rapidly because they have a low activation barrier too. So now what happens is this electron pair comes in a sense, expels phenol. So from the right-hand piece here, what you get is you get phenol. So that's one of the products. And from the right-hand piece, you end up with a conjugate acid of, you guessed it, acetone. And so this process gives you both two very useful products. It gives you phenol and it gives you acetone. And it makes use of chemistry that you can easily understand, right? I mean, these are the types of reactions that we've talked about all throughout the semester. So this is the industrial synthesis of phenol and inter-alia acetone. For those of you who walked in late, question and answer tomorrow at 11. So I don't have to say anything. Okay, so let's review a little bit of what we learned in chapter 18. Chapter 18 is a long and challenging chapter, and there was a lot of very new material for us that we need to kind of put into some kind of organization. Now, one of the things that we talked about in this chapter was electrophilic aromatic substitution of phenols. In fact, we talked about reactions of phenols. You can think of phenols as being either aromatic rings or alcohols, and in fact, they're both, right? I mean, you have a hydroxy group, so it's an alcohol. You have a benzene ring, so it's an aromatic ring. And so the chemistry that they will participate in is combined of both. So let's talk about the benzene-like chemistry. What kinds of reactions characterize benzene rings? Well, benzene rings, as you know, are not like alkenes, really. So in order to get a substitution on a benzene ring, you really need to have an electrophilic aromatic substitution process, which involves the addition of an electrophile and loss of a proton. That process is much easier, faster, if the benzene ring is electron rich. Phenols are electron rich species, and more to the point, they are easily converted to phenoxides, they're conjugate bases. And so if a phenol is activated towards electrophilic aromatic substitution because of what? Because of the electron pairs on the oxygen atom, then the phenoxide, which has a full negative charge on that same oxygen atom, is even more activated towards electrophilic aromatic substitution. So phenoxides are going to be extremely reactive. And so this is something that we saw when we discussed the bromination of phenol. We said that phenol undergoes rapid bromination without the need of a Lewis acid catalyst to activate the bromine because the ring is very reactive. If you do this reaction in carbon tetrachloride or some similar kind of non-coordinating solvent, you get the monobromo compound. Then remember that if you do the same reaction, if you do the same reaction in water, you get a different product. You get quantitatively rapidly this tribromophenols. And the reason for that is that in water you end up, two reasons really. One reason is that in water you end up activating the bromine. So you figure the water playing a role, with different mechanism, granted, that the same kind of role that the Lewis acid did in other electrophilic aromatic substitutions. You have more reactive source of the electrophile, and you have a more reactive source of the benzene ring, because in water you have at equilibrium a small amount of that phenoxide that is really, really reactive. And so for both reasons, the electrophilic aromatic substitution chemistry of phenols is faster than for benzene rings. Now, we talked also about the fact that you can do nitrations of benzene rings. And the nitrations are not nearly as easy to do, because if you try to nitrate a phenol directly, it turns out nitric acid can oxidize the phenol to quinone. And so you end up with mixtures of products. So the way you get around that is you come at it, as I said, in the opposite way. You take a chloride. This chlorine stands in for a hydroxy group. You introduce the nitro groups, and then you do a nucleophilic aromatic substitution to get your phenol, to get your hydroxy in there. So it's just an indirect way of doing what you wanted to do. Phenolic ethers are easy to form. You can form these because phenol is a better nucleophile. I'm sorry, phenoxide is a better nucleophile than phenol. Why is that? Well, because the oxygen has a negative charge. And so doing a Williamson ether synthesis with phenoxide is really easy. You take the phenol, you deprotonate it, and then you just add your electrophile, and you get the phenyl-alkyl ether. Now, it turns out the reverse process, where you take a phenyl-alkyl ether and chop off the alkyl group, that's easy too. And the way you do that is kind of the same way that we've seen in the past. We've seen this chemistry in aliphatic systems, where you activate the oxygen by proton transfer, so you now render this left-hand piece of molecules a good leaving group, and then bromide from the HBr does the SN2 reaction, giving you methyl bromide and phenol. And so this chemistry, both going from phenol to ether and ether back to phenol, that's easy stuff to do, not hard. I mentioned that you can do it not just with HBr, but with BBr3 and aluminum chloride. The mechanism is the same. These are Lewis acids, and so one of the electron pairs on the oxygen atom engages the Lewis acid, and then nucleophilic addition takes place. So it's essentially the same. Okay, so that was kind of what we talked about with respect to electrophilic aromatic substitution of phenols. Now, the other thing we mentioned was that not only for aromatic bromides, but also for vinyl bromides, or aliphatic, for compounds like ethylene bromide, you don't get an SN2 on an sp2. Okay, so it's kind of something. This is something you kind of are. They drill this into you in this class. No SN2 on sp2. This kind of reaction really doesn't take place. And we mentioned the reasons for this. Primarily, well, the big reason is that the transition state that you would have to reach to do this is high in energy. And so, and that's for a couple of reasons, because the carbon at the transition state would be sp hybridized, and also because there's a steric problem in approaching that back carbon atom. Now that's what happens with a CC double bond. With a benzene ring, it's much, much worse. And the reason it's worse is because if you try to do an SN2 here, you would have the nucleophile attacking from inside the ring where it can't be, right? And so there's no way to get the nucleophile oriented correctly. And even if you're somehow magically able to do that, you would get an inversion of the stereochemistry here, and that would give you a trans double bond in this ring. That's just not possible in any way at all. And so the first thing you think of is that, well, I can't do SN2, maybe you can do SN1. But for similar reasons, SN1 chemistry doesn't work either. And so I can't do SN2, I can't do SN1 on benzene rings or on vinyl halides. So then how does one explain what looks very much like an SN2 reaction at first glance. So when you first see this reaction, people, well, you just told me that I can't do an SN2, but here it is. I have a strong nucleophile, methoxide. I have a carbon atom right there that has a leaving group. There it is, fluoride. And I allow these to react, and I end up with a displacement. And that looks very much like an SN2, but it's not. And the reason you know it's not is for a couple of things. First of all, there's this very surprising rate acceleration, huge rate acceleration as I increase the number of electron withdrawing groups. Second of all, if I don't have the electron withdrawing groups, nothing happens. So clearly, these electron withdrawing groups are doing something to accelerate the reaction. Also, and even more surprising, is that the normal trend for rates in SN2 and SN1 reactions are iodides faster than bromides faster than chlorides. Chlorides almost unreactive. Turns out in this reaction, it's completely the opposite. Fluorides are the most reactive. Now, that immediately tells you what's going on. Because in the SN2 reaction, the reason fluorides are unreactive is because the carbon-fluorine bond is strong, and the carbon-fluorine bond is being broken in the rate-determining step. And so in the rate-determining step, you're trying to break a really strong bond. Activation energy goes way up. If you're trying to break a carbon-iodine bond, which is much weaker, then the activation energy is much lower. Okay, here, something else is happening. Because if that were happening here, then the fluoride would be the slow one, but it's not, it's the fast one. So that tells you that you're not breaking this bond in the rate-determining step. And it suggests very strongly that actually getting a different kind of mechanism than the SN2. The SN2 is concerted. Here you have a stepwise mechanism where you do an addition, which is rate-determining, and then an elimination of the fluoride. So the addition step, where the nucleophile attacks the electron-poor ring, that's going to be the slow step. Why is that the slow step? Because it's the step where you disrupt the aromatistics. That costs you the energy. You lose the aromatic stabilization. And then the second step is much faster because here you're restoring the stabilization. Now, the reason the fluoride is faster than the fluoride is because the fluoride is more electron withdrawing. So the more positive charge you have this carbon, the faster the first step. And so this is the mechanism of the nucleophilic aromatic substitution. Very different than what we've seen before. This is now a addition elimination. You add the nucleophile first, then you eliminate the leaving one. Okay, now. The next part of the chapter was, we talked about oxidations of phenols and their alcohol type reactions. And remember that alcohols undergo an oxidation based on loss of the alpha hydrogen here. And so if you don't have an alpha hydrogen, if you have tertiary alcohol, it doesn't oxidize. So tertiary butanol inert to chromium +6. But phenols, nonetheless, are easily oxidized to quinones. And the reason for that is because, once again, there's a slightly different mechanism. You end up pulling off one hydrogen atom to form a radical, oxygen-centered radical, and then you pull off the other hydrogen atom, and then you end up that radical is actually the resonance structure for the p-benzoquinone. And so quinone formation is very, very easy, not just from phenol, but also from other aromatics. The example we gave was anthracene. And whether you have the diol, the monoalkyl, or interestingly enough, even the hydrocarbon, strong oxidant will oxidize each of these compounds to a quinone. And in this case, it's going to be just the anthraquinone. So there's the anthraquinone. So you end up oxidizing the central ring. It turns out that this anthraquinone piece is central to a number of important natural products that are derived from cultures of Streptomyces. So Streptomyces are a soil fungus that does some very interesting chemistry and that provides a lot of compounds that are used in pharmaceuticals. So Erythromycin was just one of these. So that kind of tells us a bit about what goes on with the chemistry of phenols. But in this chapter, we also talked about a different kind of aromatic substitution chemistry that relies on transition metal catalysis. And this allowed us to explore just a little bit, scratch the surface really, of transition metal organometallic chemistry. So let's go over this new area one more time. And recall that you have valence electrons in these numbers in the third row, and then and you don't have to memorize these, of course. But these valence electrons tell you something about the reactivity. A lot of the reactions that we look at are in this column here, nickel, palladium, platinum, which are all D10 compounds. And so the Heck reaction was the one that we discussed first. And this allows you to form carbon-carbon bonds between sp2 hybridized carbons. Okay, so these reactions are particularly good for sp2 to sp2. Now it turns out that we saw at the end of the discussion, we also saw in the Stille reaction, we saw sp2 to sp3. Those are less common, and the reason they're less common is because of that beta hydride elimination problem I mentioned. sp3 are really tough. Okay, so there it's really difficult. sp and sp2, no problem, because again, no beta hydride elimination. You end up mixing an aryl bromide with an alkene in the presence of a small amount of palladium 0 and catalytic amount, and you end up with a very good yield of this styrene. And the first time you look at this, you think, boy, how the heck did that happen? Because look, that you guys didn't get it because you're not listening. You wonder how it happened because the ethylene is not functionalized. I mean, this is something we've not seen before, right? Usually when we form a carbon-carbon bond, you have functionality on both of the reacting carbon atoms. Here, one of the carbon atoms is functionalized, the bromide, the aryl bromide. The other one isn't. Okay, so clearly something strange is going on here. And so in order to see what's going on, we discussed a little bit about what these ligands look like. And we distinguished L ligands like triphenylphosphine, ammonia, and others, which are neutral if they're pulled off the metal. Okay, so L ligands are going to be neutral. If I take the metal, the L ligand, pull the L ligand apart, that L ligand is a neutral molecule. If I have an X ligand and I have it bonded to the metal, I pulled off the metal, then that X ligand is going to be an X minus, it's going to be an anion. And so chloride is an X ligand, and triphenylphosphine is an L ligand. Okay, so and then we talked about different kinds of X and L ligands, and then we talked about the oxidation state of a metal. Now, oxidation states of the metal are important because they give us some clues about the mechanism, and it's very, very easy to figure out what the oxidation state is. All you do is you count up the number of X ligands. And if the metal is charged, it has a plus charge, then one plus charge, then you add that plus charge to the oxidation state. It's got minus charge, then you subtract that from the oxidation state. It kind of makes sense because it does a minus charge, means it has added electrons that you have to take into account when you figure out what the oxidation state is. You need to be able to go through and figure out oxidation states. It isn't particularly hard. We talked also about the EN notation. And so for tetrakis, phosphine, palladium, this is going to be 10 because this is a D10 compound, and the oxidation state here is 0. And so you take the valence electrons, which is 10, oxidation state 0, and that's a D10 compound. Okay, so we then talked a little bit about the hybridization, just so we understand what the shapes of these molecules are. The hybridization of transition metals, it kind of follows the same logic that we discussed for carbon. It's just that you've got more orbitals because you have more electrons, and so you get more hybrid orbitals. That's essentially it. Then the important discussion was the mechanistic types. The mechanisms that these transition metal complexes participate in are a little bit different than what we're used to looking at. And so if I take our favorite palladium complex, then I can reversibly detach one or more of the L ligands. So in solution, I can have an equilibrium that has palladium 0 either with 3 ligands or with 4, okay? And now this is important because of the 18 electron rule. Remember that we have an 18, not an 8 electron rule, and that when compounds have 18 electrons, they are coordinatively saturated, and that means they can't react. So if this palladium is going to do anything, it has to lose one of these ligands so that it is now a 16 electron species that can react, okay? And so we can't exceed this 18 electron business. So this ligand association-dissociation reaction comes up again and again. Now, substitution is another common reaction, and it's typified by methyl lithium reacting with this phenyl iodopalladium compound. So the methyl, acting like a nucleophile, should remind you of an SN2 reaction, kind of displaces the iodide. So you end up with a X ligand replaced by another X ligand. So ligand substitution neither one of these reactions is particularly weird. The weird one, and the one that is central to all this, is oxidative addition. This is something you've never seen before. So if I have a 14 electron palladium 0 and this iodide, the palladium does something very strange. It inserts into this carbon-iodine bond, and in the process, the palladium goes from palladium 0 to palladium plus 2. And so when we say oxidative addition, we're looking at it from the point of view of a metal, okay? So when we talk about oxidations, very often, we think about oxidizing an alcohol to a ketone or whatever. Here, we're not talking about alcohol to ketone. We're talking about oxidizing the metal from 0 to plus 2 oxidation states. So the way this happens is as follows. You end up with palladium doing two things. Donating electron density from its filled d orbitals into the empty sigma star of the carbon-iodine bond, and then the filled sigma orbital donates electrons back into the palladium into one of the empty hybrids. And so you end up in both ways, you end up weakening that sigma bond. So you have electrons going into the antibonding orbital, weakening it, and then electrons from the bonding orbital going into the palladium, again weakening it. In the process, breaking that bond and performing that oxidative addition. Now, that is the heart of a lot of this chemistry. The reverse process is also known, reductive elimination, where you have two, in this case, X-type ligands that form a bond, the red bond here, and in the process give you from nickel 2 a nickel 0. So the nickel is being reduced at the time that you're eliminating two of these ligands. So all of these reactions that we talked about, these couplings, the Heck reaction, the Suzuki, the Stille, and one of the problems in Negishi, I knew that Negishi was discussed, it's one of the problems at the end of the chapter. All of those reactions depend on a catalytic cycle that involves successive oxidative addition, reductive elimination. So you go palladium 0, palladium 2, that's the oxidative addition, reductive elimination, palladium 0, and then again. And then the catalyst can cycle that way. Ligand insertion was another mechanism that we saw. This is a one ligand insertion where this methyl group inserts into that carbonyl. A 1,2 insertion of this type. This is one of the steps in the Heck reaction, where you have a vinyl ligand on the palladium. Remember that the vinyl group can act as a L-type ligand, and so the phenyl inserts, and you end up with a new carbon-carbon bond being formed. Okay, so. The beta hydride elimination was the last of the mechanisms that we talked about. This again is one of the steps in the Heck reaction, but it's usually not one of the steps that you want. Usually beta hydride elimination is one of the steps that screws things up for you because it changes the because it then will give you an intermediate that's not on the catalytic cycle. Now it turns out this is on the catalytic cycle for the Heck reaction, but it's not for Suzuki and for the others. Okay, so this kind of opens up a whole universe of chemistry that we're not going to explore in this class, but a very important one. So we talked briefly about the Heck reaction, and we went through the mechanism. Now, with this and with every other mechanism, you absolutely, positively have to reproduce this on a piece of paper on your own without looking at your notes or the book. If you can do that, you understand what's going on. If you can't do that, you don't. It's that simple, I'm afraid. So you need to make sure that these steps make sense to you. The first couple of steps are just ligand association-dissociation equilibria. Then you get an oxidative addition. Then you lose another ligand. You add the vinyl as another L-type ligand. Then you get the 1,2 insertion, a beta elimination, and then loss of another ligand exchange. And then in the last step, the base tetrad, in this case triethylamine, removes HBr from this and gives you back your palladium 0 catalyst. And so these are the elementary steps of the Heck reaction. It looks complicated until you recognize that really it's just putting together all of these elementary steps that we talked about, no one of which is particularly hard, with the exception of the oxidative addition. The oxidative addition is the hard one to understand. So that is this step here. Okay, so this is the Heck reaction. The Suzuki reaction, which we talked about, is just a little bit different because now it looks a little bit more familiar because now you have two functionalized carbon atoms that are coming together. And so if you're going to do a Suzuki reaction, you still have the bromide or iodide or triflate, as we saw at the end of the chapter. And then the other reactant is this boronic acid. Boric acid would be 3 hydroxy groups. If one of those hydroxy groups is replaced by an arrow or an alkyl and some boronic acid. You still use palladium 0 as a catalyst, and always hydroxide. Now I said palladium 0, and you look at palladium acid and you say, this is palladium plus 2, what's going on? Why is it palladium plus 2? Well, because the two ligands are X-type ligands. If I take acetate away from the palladium, it's acetate with a negative charge. And so I have 2 of those, so that's going to be a plus 2 palladium. Now, as it turns out, palladium is weird. And palladium can undergo, palladium plus 2 can be easily reduced to palladium 0 by stuff that you don't think of as a reducing agent. Triphenylphosphine does a great job with that. But also, in this case, the triethylamine they have triphenylphosphine. Okay, so triphenylphosphine is reducing that. Sometimes triethylamine can do that too. Okay, so the carbon-carbon bond between sp2 and sp2 is this red one right here. Now, how does this work? Well, it works pretty much the same way. I mean, the mechanism is essentially the same as what we saw for the Heck reaction, but with a little twist, okay? So you end up decomplexing two ligands from the palladium to get a palladium 0 that's a 14 electron reactive complex. That does your oxidative addition. Then you get a ligand exchange. Hydroxide displaces bromide. And that turns out to be important because the hydroxide acts as a nucleophile in the next step. And so you end up forming an oxygen-boron bond. And in that process, you end up putting a negative charge on the boron. Remember the boron's electron pair acceptor? Now that negative charge activates this boron-carbon bond. This is now electron rich, so it migrates. So you end up with a ligand substitution reaction of a type that gives you the complex that then does the reductive elimination. And so this step is a little bit different from the others that we've seen. So we talked about the Stille reaction. The Stille reaction is the same as all of these. You end up generating your 14 electron species. The Stille reaction works with aryl bromides or iodides, rarely with chloride. It also works with triphlates. So you get your oxidative addition, then you get a ligand exchange. The tin compound does another ligand exchange, and then reductive elimination gives you your product. So all of these reactions are very, very similar. Not much to distinguish the Stille, the Heck, and the Suzuki. One of the problems at the end of the chapter is the Negishi reaction. That looks very much like this. Instead of having a tin, you got a zinc. Not much difference. There was a different reaction that we talked about, a different organometallic reaction, and that was the metathesis reaction. And recall that we have these rather exotic-looking organometallic complexes, typically of ruthenium, where I have a carbene attached. That's a carbon with two bonds to a metal, and tricyclohexyl phosphines, or in the other drugs catalyst, I have a stable N-heterocyclic carbene as a ligand. And these are L-type ligands. So without going through the structures of the catalysts, these metathesis catalysts can do something that looks, magical. They can take two alkenes and stitch them together in this way. So in this case, I use 2 mole% of the drugs 1 catalyst, you heat it up, and this is an equilibrium, but the equilibrium is driven by loss of ethylene as a gas, so you drive the equilibrium from here to there. And so it looks as if these 2 carbon atoms are holding hands, and then these 2 carbon atoms are there, and in the process I formed a ring. Now this is a very strange reaction, and you can ask yourself, well, instead of forming a ring, why didn't I get a linear polymer? And the answer to that is because the linear polymer requires 2 of these to come together, whereas forming the ring is a unimolecular process. So you can always control that partitioning by concentration. In other words, if I do a reaction at a really low concentration, then the only reaction that's going to take place is the intermolecular one. And if I do the reaction at a high concentration, then I have a much higher probability of getting the bimolecular process to take place. And that's how you control this. So how this works is by this weird mechanism where you form a 4-membered ring that involves the ruthenium catalyst. And so you end up with the carbene and the alkene. You form this 4-membered ring, and then the 4-membered ring falls apart. Now, if you look at the 4-membered ring, here's how you look at it to understand this maybe a little better. Let's peel away all the substituents here and take a look. So here's your metal, and I have an R1 and an R2. Okay, let's just put it that way. Now, this ring can fall apart in 2 ways. It can fall apart this way, right? And if it falls apart this way, then I have the metal, and I have this carbene, and I have this alkene. Or it could have fallen apart in a different way. It could have fallen apart in this way. And if it did that, then I would have ended up with this carbene and this alkene. Okay? So that's at the heart of it. The mechanism involves reversible formation and cleavage of that four-membered ring cycle. And when you do that enough times, you end up forming the products that are shown. To see that, you really have to go through the mechanism and convince yourselves that is in fact the case. Your text points out that if I start out with two different alkenes that are substituted at both ends with different things, I end up with 8 products plus 2 starting materials. And so at first glance you say, well, this reaction has to be totally worthless because if it's going to give me 10 different things, how useful can it be? And yet, if you go through the problems, you'll find out that the answer to that is very useful because you can control how the reaction evolves in various ways. Okay, that was pretty much what I wanted to say in terms of review of chapter 18. We're now going to enter chapters 19, 20, and 21. And these I kind of lumped together because they all involve carbonyl chemistry. So this is going to be, we're going to be talking from now on about chemistry of various types of carbonyl groups. And this turns out to be at the very heart of organic chemistry. A lot of the chemistry that goes on in biological systems involves carbonyls. It's sort of the most important, so carbonyls, ketones, aldehydes, carboxylic acids, esters. These are all going to be the most important functional groups that we encounter. And you'll see that the chemistry starts out, from simple concepts, and then putting 2 or 3 of these very simple concepts together allows you to build complexity rapidly. Now, the chemistry is not hard to understand, fortunately, because it makes use of concepts that we've seen all along. So for chapter 19, you're going to see that the chemistry of ketones and aldehydes really, doesn't introduce a whole bunch of stuff that's wildly new. I mean, the organometallic chemistry that we talked about, Heck reactions, yeah, that's new, you never see anything like it. This stuff, we've seen stuff that's pretty close to this. Okay. So we need to know what we're talking about. And so unfortunately we have to spend just a little bit of time talking about nomenclature. So if we're talking about ketones, we're talking about this kind of structure where these two groups don't have to be the same. They can be either an alkyl or an aryl. So the carbon that is bonded to the carbonyl can be either sp3, sp2, or even sp, but it has to be a carbon. Okay? And these are going to be ketones. Now, if one of the groups here is a hydrogen, then that's an aldehyde. And so what distinguishes ketones from aldehydes is that in one case you got a hydrogen, in the other case you don't. And so it's that simple. Now, this pi bond, this carbon-oxygen pi bond, is shorter and stronger than an alkenes. So it looks like an alkene, but no, it's shorter, stronger, and what's going to be very important for the reactivity is it's more strongly polarized. And it's polarized in this way, with the negative end on the electronegative oxygen atom. And so whenever you look at one of these ketones or aldehydes, what you want to see is a positively charged carbon atom where I'm pointing. So a carbonyl carbon has a partial positive charge. Now, and the oxygen has a partial negative charge. So, guess what? The oxygen atom will react with acids. The positively charged carbon will react with nucleophiles. So this accepts an electron pair, and this usually gives an electron pair to a proton. And that is the center of just about everything we're going to talk about. So it's that simple. Positively charged carbon reacts with nucleophiles. Oxygen atom reacts with protons, Lewis acids, and so on. Simple. Okay, so we're going to be looking at various aspects of carbonyl chemistry for quite some time. So let's talk a little bit about nomenclature. This is the subject that's boring, but we need to talk a little bit. Turns out these compounds have been known for a long time. They were known at a time when we didn't really have any kind of systematic nomenclature, and so like a lot of the aromatic compounds that we saw, phenol, resveratrol, there are all these idiosyncratic names that unfortunately we need to remember. So acetone, you all know, nail polish remover. Acetophenone. Okay, so anything that says phenone is a phenylketone, right? So benzophenone, acetophenone. Okay, so acetophenone. If I had another carbon here, that would have been propiophenone. And if I had another one, it would be butyrylphenol. Okay, so acetophenone is this stuff. This stuff smells really good. Cinnamaldehyde. You know what it smells like. So if you open a bottle of cinnamaldehyde, you take a whiff of it, you immediately recognize cinnamon. Now it doesn't smell, you can tell it's not cinnamon, because cinnamon is a much more complex odor, because it's got not just cinnamaldehyde but a number of other things, but the resemblance is unmistakable. If I'm furan here, this is called furfural. This stuff comes from corn cobs. I think I mentioned that. If you pyrolyze corn cobs, you end up with furfural, and then you can do another actually organometallic reaction that extracts from here carbon monoxide. So this carbon can be lost as carbon monoxide and gives you furan. So heat this up with a nickel zero catalyst. I think it's nickel zero they use. Rhodium works too. Rhodium's expensive. You end up with furfural. With furan. So it goes. So the commercial thing goes from corn to furfural. So this is an unusual organic compound that is actually an agricultural product. And then from here it goes to furan. We've seen furan before, and carbon monoxide. And then you can hydrogenate this, and that gives you THF. Remember THF was what we used for Grignard reactions and other things? Well, that's how they get THF, they get from corn cobs. So, okay, methacrolian. Acrolian is the compound that just doesn't have the methyl. If I put methacrolian, then it's a methyl compound. These this is a compounds used in plastics manufacturing. Okay, so there's some groups we need to remember the names of, and the nasty one is benzoyl. Okay, so this is benzoyl, and the O is red because it's not a benzyl. Okay, so this is benzyl, that's benzoyl. Gee, why did they make confusing nomenclature? Don't ask me, I didn't do it, okay? So benzoyl is the compound that has the group that has the carbonyl. Benzyl doesn't. Formial, formic acid, acetyl, acetic acid, propional, propionic acid, and so on. So these are groups that we kind of need to know the structure of. Substitutive nomenclature. Again, I'm not going to make a big deal over this, but you do need to be able to take names and convert them to structures. Structures to names, yeah, you need to be able to do that too, but really, names to structures, that should be second nature to you. The structure of the name is harder. There are a few problems in the text. I would suggest you do them. Remember that we have these groups that give us priorities. So if you have an aldehyde in the molecule, then that's a principal group, and the compound's going to be named as an aldehyde. Aldehyde takes priority over ketone, takes priority over alcohol, takes priority over thiol. Remember, if you have none of those, then it's the number of double bonds and then triple bonds. And so, why does aldehyde have priority over ketone? No rhyme, no reason. That's just a rule. Okay, so, you know, it's not a lot of things. The suffix for aldehydes is al, al. So this would be, you know, 1, 2, 3, 4, 5, this is pentanal. Now notice that because an aldehyde, I don't need a number. Because there's a hydrogen here, it means that the carbonyl is going to be at the end. So there's only one pentanal. On the other hand, there are going to be two pentanols, right? So if I had a pentanone, it's either going to be a 3-pentanone, or if the ketone is over here, that would be a 2-pentanone. But if it's pentanal, there's only one pentanol possible. So I don't need to designate which carbon atom is the formyl carbon atom, right? Remember, this is the formyl group. So I don't have to designate that. That's the end carbon atom. But when I go to ketone, yeah, I do. Now, if it's a cyclic ketone, then it's going to be cyclohexanone. And the carbonyl carbon is carbon atom 1. So this would be a 2-methyl cyclohexanone. The methyl over here would be 3-methyl and so on. If I have 2 ketones, then it's not an one, it's a dione. And if I had 2 aldehydes, it would be a dial. Okay, if I had 3 aldehydes, a trial. Not trial, trial. Okay? And spell the same thing. So this would be a 1,3 cyclohexane dione. Okay? There's 1,4 cyclohexane dione. Now, if you have a ring and you have a substituent that's the aldehyde, then you can use this carbaldehyde. So this would be cyclohexane carbaldehyde. Very often you'll see this as carboxaldehyde. Carbaldehyde is preferred. Carboxaldehyde is what everyone uses. Okay, so we'll pick up on Monday.